Welcome to this seminar. Welcome Abolfazl Simorg to the talk. He's assistant professor with us at the Aerospace Department of UC3M. He did his bachelor and master thesis in control engineering, and then did his PhD here. I was his supervisor indeed. His research, he has also done a research stay at TU Delft. The topic of his thesis is related to aviation and climate impact and optimal control and trajectory optimization. So you will probably listen and hear about it. And his research interests include not only aircraft trajectory optimization and ATM research and climate impact, but also mathematical control theory, optimal control, and robust control, and I believe model predictive control as well, right? He has been working in multiple European projects and developed some state-of-the-art open source libraries, and he has received several distinctions, including the Luis Azcárraga Award by ENAIRE in 2023, and recently, last week, he was second in the César Young Scientist Award at European level. So congrats for that, Abolfazl. And well, floor is yours. All the best.
Thank you very much, Manuel, for the introduction. Well, I'm Abolfazl Simorg, and today I'm going to talk about climate impact of aviation and mitigation measures. So let's talk about climate change, which is no longer a future threat. It's already here, and we can see the effects in terms of rising sea level or more frequent extreme weather events. To prevent irreversible climate impacts, it's essential to limit the global warming to well below 2 degrees, if possible 1.5, established during Paris Agreement. And this increase in global warming is compared to pre-industrial levels. So, but as can be seen here, we are already above 1.5 degrees limit, meaning that we need to take actions urgently over all sectors. Here we can see the trend of greenhouse gas emissions over the past 30 years. The red line here shows that we are constantly reducing emissions. And in 2022, compared to 1990, we are reducing emissions up to 31%. But the EU has set goal to go for 55% reduction in 2030 compared to the reference here. If you look into the contribution from transportation, and in particular aviation, we see no improvements, meaning that we need to urgently take some actions if we want to meet the goals, the climate goals, such as here, the EU target. So it's important, and aviation needs to do something. Before presenting the potential mitigation measures, let's see how aviation is contributing to climate change. Well, aviation is contributing to climate change through the emission of carbon dioxide, which is a well-known species, the most well-known, but also through other non-CO₂ effects, such as emission of water vapor emission, which is a greenhouse gas, nitrogen oxide effects, and the atmospheric concentration of methane, ozone, and also other indirect effects. And also we have aerosols and contrail, which is the most visible and the largest contributor to climate change. Here we can see the formation of contrails, normally at high altitudes. This is what we normally see, especially during winter, if the weather is not cloudy because of specific meteorological conditions. So all these species, CO₂ and non-CO₂, change the radiative balance of the air, so they contribute to climate change. For example, in terms of contrail, they reflect incoming solar radiation during daytime and trap also outgoing long-wave radiation from Earth, so they can have cooling or warming effect. But during nighttime, they only trap outgoing long-wave radiation from Earth, so it has warming effects. So let's see the mitigation measures. There are many, such as technological solutions, hybrid electric aircraft, hydrogen-powered aircraft, alternative fuels such as SAF, sustainable aviation fuel, we have some market-based instruments such as European Emission Trading System or CORSIA, which basically they provide incentives toward adoption of a climate-friendly technology or operations. And but these measures are mostly focused on CO2. They can provide benefits for non-CO2, some of them, but the issue is that most of them are medium to long-term measures. In terms of non-CO2 effects, which is claimed to be responsible for 2/3 of aviation effective radiative forcing, so climate change, we have flight planning and operational measure. So the non-CO2 effects of aviation, such as contrails, as we saw, they have a strong dependency on the time and location of emission. So we can identify climate-sensitive areas, like these areas, and we reroute them to mitigate the corresponding effects. This is an immediate solution, relatively, so it's shorter term compared to others, and it's feasible with existing infrastructure. So my thesis was mainly focused on this one, and this is what I'm going to devote half of my presentation to it. So climate-optimized flight planning to mitigate climate impact, considering also potential uncertainty effects. So let's see the climate-optimized flight planning. Basically, imagine we have 2 points that we want to fly, so from an origin A to destination B. And in order to plan efficient trajectory, we need to feasible and efficient. We need to consider some sets of constraints, such as dynamical constraints to model aircraft dynamical behavior, flight envelope or operational constraint, and flight planning objective, which is now more important for us because we are going to have flight plan that is climate optimal. So if the objective is cost, we normally go for shortest path, like this. But if the objective is climate, we first need areas of airspace where the aircraft emissions have large impact in terms of climate. And climate-sensitive areas, when we include it into the flight planning, then we reroute it to mitigate the corresponding effects. So normally there are, at the time of my PhD, there were 2 models to use to identify climate-sensitive areas, so to model these areas. One of them is ACCF and the other one COSIP. I'm going to talk about them a lot during this presentation. So yeah, there are 2 models. There were 2 models that time to account for climate-sensitive areas. So we see that it's easy. It seems easy that we have climate-sensitive areas and we reroute that and we mitigate climate impact. But what is the actual potential of flight planning to mitigate climate impact? We first need to consider the high uncertainty associated with non-CO2 effects. So these climate-sensitive areas, they are highly uncertain to identify. So we cannot, for example, for this case, we reroute these areas. But what if the climate hotspot be here? So the rerouted one crosses climate hotspot. Or what if the hotspot that we were using to reroute was cooling one? So what happens? Basically, if we do not account for such uncertainty in the flight planning, we will increase the operational cost. Why? Because we are deviating from shortest path. We are increasing CO2 emissions because we most likely burn more fuel because we are deviating from shortest path. And also we may degrade ATM performance. We are avoiding flying specific areas, so we may make specific areas congested, increasing complexity or ATC workload. So we need to be more confident when we are rerouting aircraft trajectory in a climate-friendly manner. And so this was one of the aspects for answering this question. And the other one is that these climate-sensitive areas are highly dependent on the meteorological background conditions. So in particular days, we may not find any climate-sensitive areas. So flight planning cannot provide anything because we may not need to reroute. But in particular days, we may find a hotspot covering whole Europe. So it's important to consider a large set of weather patterns when we want to report the potential mitigation of flight planning in reducing climate impact. So we need to perform large-scale analysis, so covering a wide range of weather patterns. Here we can see a state-of-the-art on climate-optimized flight planning, and as we can see that all the studies were performed in a deterministic manner, ignoring uncertainty, so they could lead to ineffective trajectories. And we can see that all the studies were performed in unconstrained airspace, or we call it a fully free routing airspace. And the reason is mainly because of complexity if we want to consider the current structure airspace. In unconstrained airspace or fully free routing, the optimization is fully continuous, so it's easier to solve. But in structural airspace, we have hybrid decision space, so it's difficult to treat. And basically, the mitigation reported were not that reliable because it is not flyable, such routing. And if you look at the case studies, they were performed on limited number of case studies, so they were not statistically relevant, I would say. So they do not offer a basis for developing basically indicators for incentivizing stakeholders toward adoption of climate optimized routing. Well, we set several goals. First, to identify the most relevant sources of uncertainty affecting climate impact estimates. Where we found meteorological uncertainty or weather forecast uncertainty and uncertainty due to having multiple climate impact estimates. Then after identifying uncertainty, we aim to develop robust flight planning tools capable of incorporating uncertainty in order to plan climate optimized route. And we developed two tools, Roost and RAG, which I'm going to present in the next slides. And finally, providing insight into the mitigation potential achievable through flight planning by performing large-scale analysis. So addressing all these gaps, basically. So let's start with uncertainty effects. We consider two sources of uncertainty. The first one is uncertainty due to having multiple climate impact estimates. As mentioned in the beginning of the presentation, we had two models at that time, COSIP and ACCF. Ideally, they should provide consistent estimates because we need to have them to be consistent. So here we can see an example of the first row here shows the contrail climate impact or contrail climate sensitive areas with one model, so the COSIP, midnight and midday. And also the second row shows the contrail climate sensitive areas with ACCF, another model. And if we see there is a large discrepancy in particular areas. For example, here you have cooling, warming, or here it's warming completely, but here we can see cooling effects. And why is it important? If we use, for example, COSIP for flight planning, then here, if the flight crosses this area, we may need to reroute it to avoid forming warming contrails. But what if the reality is this one? What happens? We are even increasing the climate impact. We are rerouting cooling areas. So it's important to consider such discrepancy in planning climate optimized routes. Another one is due to meteorological uncertainty. We know that weather forecast is never perfect. So this can result in uncertainty in the climate impact estimates because the models, these two models require specific meteorological data such as relative humidity, temperature, so all these values to provide climate impact estimates. How we accounted for that one, we basically use ensemble weather forecast. It's a state-of-the-art framework in numerical weather forecasting, which instead of one deterministic forecast, it provides multiple probable forecasts, for example, 50 normally. And here we can see what happens basically. So here in particular day, we have two relative humidity. So two members. This member is the probable weather situation and obtained from this ensemble weather forecast. So we have two potential relative humidity, member 1 and member 2. And if we look what happens in persistent contrail forming areas in which where we fly we create contrails. And we see that large, not large, but we see difference between them. And if we use this area in the flight planning, we reroute this, but what if the reality be this one? So we still have contrails. So these two sources of uncertainties are what we considered in the optimization. So trying to have trajectory that is robust to these sources. And so after identifying the sources of uncertainty, the most relevant ones, we developed two tools. This is ROC, is for fully free routing airspace or unconstrained, so similar to previous studies. But the difference is here that we account for uncertainty related to weather forecast or having multiple climate impact estimates. I'm not going to present the maths here, but basically the idea behind this, how we accounted for uncertainty, was to augment the dynamical model of the aircraft by considering different realization of meteorological variables. So we will expand the dynamical model of the aircraft, or in control terminology, the state vector, the state space representation. Then in terms of objective function, we have operational cost and climate impact. We may use average or also the variance if we want to control the uncertainty effects. And the way that we solve it is basically through direct optimal control approach. We do the transcription, so discretize and convert it to the nonlinear programming problem, and then using well-known solvers, such as here, interior point method. And this is the type of solution that we get. I'm going to present some examples now. And it's available on GitHub, so this is an open source tool. So let's first start with the motivation, robust versus deterministic. So here we are going to optimize a flight in 13th of June, midnight flight from Belgrade to Luxembourg. And we have three optimization scenarios. So here, basically the uncertainty in the meteorological variables is obtained from ERA 5 reanalysis data, which have 10 ensemble members, or meaning that 10 potential weather scenarios. So the first optimization scenario is to perform deterministic optimization for each probable weather scenario. And then we also have our proposed robust approach to compare. So here we can see a bit complex figure for the results. I'm going to explain it. The first part, so the vertical, the horizontal axis shows the optimization scenario. So the 10 deterministic optimization for member 0, it means for weather scenario 0 or 1. It's in the Python, so it's starting from 0. Member 1 to member 9 here. And the vertical axis shows the assessment. So if we consider this as a matrix, the diagonal element shows the minimum value. What that means? It means that the assessment is only climate optimal, or the performance is good, if we use that weather scenario in the optimization. So, for example, optimization for member 1, assessment for member 1. What happens if we assess the results of optimization based on one potential weather scenario using other weather conditions? And we see that in some cases, we are even increasing the climate impact. For example, the last column shows the cost optimal performance. And here, if we check this one, we see that even we are increasing the climate impact. But our proposed robust approach, if we look at it, provides consistent benefits over all potential weather scenarios. So basically, we can reduce sensitivity to uncertainty in weather forecast by planning uncertainty-informed climate optimal routes. And this is also another example. So it's a flight from Frankfurt to Kiev. And the objective function that we use is the average operating cost. And average, so it's a weighted sum of average operating cost and average climate effects. And we have a weighting parameter, EIM, which basically tries to put importance on the climate effects. So if we increase EIM, we expect to receive trajectory that is more climate optimal. And here we can see the outputs. So this is the altitude profile. Here we have the climate impact for different forcing agents, such as contrails, water vapor, NOx emissions, and the net climate impact. So we will focus on this one. So we have several routing options. EIM means it's cost optimal, and EI50 here is climate optimal because the weight is high. And if we check for climate optimal, we are flying a bit lower. And if you look at the climate impact, here we are mitigating, and we are basically, the climate impact is negative, meaning that we are generating cooling effects, or here is basically cooling contrails. And here we can justify the result. So the altitude selected by cost optimal trajectory is this one, and the dark one is cost optimal. And we see that in the last part of the trajectory, it creates cooling contrails, and we can see it here. But in total, it's warming because also we have contribution from other forcing agents, such as NOx and water vapor emissions. But if you look at the one flown by climate optimal one, the last one here at 9 kilometers, the altitude, we are deviating from shortest path to maximize the generation of cooling contrails. And this is the mitigation that we can get. But here you see the climate impact is highly uncertain. The shaded areas is large. This is because in the optimization, we only focused on average. I skipped the part that we penalize variance, but we could penalize variance here to reduce the uncertainty. So in my thesis, there is also example on that. But yeah, so we can mitigate climate impact like this. Here is mainly through generation of cooling contrails, but also we have another example. So the other tool for flight planning that we developed is suitable for a structured airspace. So here we account for ATS route network, we account for discrete flight level changes, and it's a heuristic method parallelized on GPU, it's fast, and here instead of directly trying to optimize control and state variables, we directly try to optimize our flight plan to somehow cope with the discrete, the hybrid decision space. And here, as can be seen, the altitude looks more similar to what we actually fly today, so discrete flight levels. And here, for example, we can see the graph structure that we can see, so it can stick to a ATS route network. But this method is also capable of considering uncertainty, and the rest of my presentation would be on this method because it's fast, so we could do many things with it. Also, that one is available on GitHub. So let's see an example based on this approach. So it's another, it's also the same flight from Frankfurt to Kiev, but this is midnight. That one was midday scenario. And here, instead of EI, the weight of climate impact in the objective function, we used a simplified approach to make it more simple. So we have alpha, which varies between 1 and 0. Alpha 1 is cost optimal, and alpha 0 is climate optimal. And let's see the examples. So this is the altitude, the flight level, the fuel consumption, fuel speed, and NOx emission obtained for for different routing options. Again, for the climate optimal one, which is alpha 0 here, we fly at lower altitudes. And here we can see the climate responses. The impact of contrails, here we can see that we are mitigating it. And in terms of net climate impact, also we are mitigating the overall climate impact. And this can be also justified within the picture here. So the color map here shows the contrail sensitive areas. And This is the flight level chosen by cost optimal trajectory, this one. And as can be seen, the dark one crosses some warming areas. And here we can see it, and the level of uncertainty is also large. And for the climate optimal one, we are deciding to fly lower at flight level 280, which is low. And we see that we are not creating contrails, and the result is almost deterministic. So this is how we can basically try to obtain routes that are climate optimal. So far, what I presented is focused on meteorological uncertainty, but in the beginning I mentioned we are going to consider two sources of uncertainty: having multiple climate impact estimates and meteorological uncertainty. Here we consider both at the same time. So it's a scenario in March, midday scenario, and top 150 routes in Europe. And we are going to consider weather uncertainty through considering 10 ensemble members and two climate impact estimation models, COSIP and ACCF. Here we can see the results. So I'm going to start one by one. So this one is the cost optimal trajectory. And this cost optimal trajectory is business as usual. And the red area here shows the formed warming contrails along route, and the blue one shows the formed contrails, the cooling contrails along. So this is evaluation based on one of the models based on COSIP. So this is cost optimal. And we see some areas we have cooling and some areas we have warming effects. And let's see the evaluation based on another model, the other model. So ACCF. We see mismatches basically. For example, here we have warming and here we have cooling. And this is what we expected in the beginning. And here we show only the discrepancy between the generated contrails. So if one of them quantify cooling impact and the other one warming impact, or the way around. So shown here. Now let's see optimization. So that one was cost optimal trajectory. Let's see how climate optimal look like here. So this is climate optimal, but based on COSIP and evaluated based on the same model. And we see we are avoiding forming most of the times warming contrails, and we try to maximize the generation of cooling contrails because mathematically it's desired. But for the same routing option, so optimization based on COSIP, but evaluated using another model, we see that in many areas we are seeing warming contrails. And if you look at the mismatches, it's also large. So the mismatches between the model. Now let's see our proposed approach. And it's clear that the patterns look more similar and the discrepancy is almost negligible. So this shows the motivation of our study. And yeah, most of the time. So how it works basically, if one model estimates cooling and the other model warming, it tries to avoid from contrails. If both quantify warming, it also avoids to generate contrails. But if both says it's cooling, it goes for that. And we can see that it tries to keep. Also, we can see some mismatches, but this is because in the optimization, we consider it as soft constraint. So, and it's also reasonable. And so, yeah, in the beginning, also I mentioned that in order to provide incentives for stakeholders to take action toward adopting climate optimized routes, we need to perform large-scale analysis. And basically, we try to address all these questions. I'm not going to through all of them, but basically, what is the mitigation of the climate impact? What is the associated operational cost increase? How many flights we need to reroute? Is there any dependency, seasonal dependency? Or, what happens to the flight profiles? Do we normally fly lower? So to answer all these questions, we had to perform large-scale analysis. And this is, we performed several large-scale analyses, but I'm going to here present only briefly one of them, which has been published. So we consider here all days in 2022, and we consider 150 top European routes. And the model is only ACCF, so we consider only one of the models. And yeah, we consider also meteorological uncertainty. And here we can see the achieved mitigation potential and its trade-off with operating cost over different months in 2022. As can be seen, the mitigation is highly variable, and this implies the high dependency of the non-CO₂ climate effects to meteorological conditions. And for example, we can see that during summer, we see normally the lowest potential for climate impact mitigation, and this is mainly due to the meteorological condition, which is not favorable normally for the formation of contrails. But in some, for example, here in November, we have large mitigation. And here also we can see the daily variability of the mitigation potential. Here we have three routing options: the cost optimal, climate optimal, allowing for 0.2% increase in the operational cost, and we have another one, climate optimal, but allowing for 2%. The more we allow the optimizer so basically, if we allow for a higher operational cost, we expect to get routes that are more climate optimal. And here we can see also, this is the figure shows the difference from cost optimal trajectory, the performance in terms of climate impact. And we see that the green one shows the highest, and on average is 21.3%. So we can mitigate climate impact around 22% by allowing for 2.0% increase in the operational cost. There were many conclusions, but here I'm summarizing the most relevant ones for what I've presented. So basically, we saw that flight planning can mitigate climate impact, primarily through contrails, and the mitigation as high seasonal variability, and it's in trade-off with operational cost, and there can be a large discrepancy between multiple climate impact estimates, which can critically affect the effectiveness of the trajectory. And we saw that the confidence level in the achieved mitigation potential can be increased or enhanced by planning uncertainty-aware climate-informed trajectory. And also, normally the flight the aircraft tends to fly lower for climate optimal routing option. So so far, but I've been presenting was mainly focused on flight planning as a short-term measure to mitigate climate impact. But in order to address climate neutrality goals, such as ICAO net zero emissions by 2050, we need other measures. And here we can see the summary of different measures, proposed technological advancement, alternative fuels. And we also have some projections like this one. I think it's small and you cannot see it clearly, but basically it tries to say how can we address net CO₂ emissions by 2050, and it's obtained through which measures. So, for example, the green one says sustainable aviation fuels, or the blue one here is associated with hydrogen. But there is one question: are such projections reliable? Well, I'm quite sure that not. And the reason is that here we can see the climate impact of the current aviation. We have the data, we have the aircraft already flying, so we have, but look at the uncertainty ranges. It's too large. How can we be sure about the effectiveness of, for example, hydrogen-powered aircraft, which is now a hot topic, and people are investing on that. And the reason is that, for example, we know that hydrogen-powered aircraft provides a clear benefit in terms of carbon dioxide. But what about these guys, non-CO₂? With hydrogen-powered aircraft, we are emitting higher water vapor, if I'm not mistaken, around 10 times higher. So we may form or create more contrails. We are not sure about the lifetime, about the impact, and that's why I'm saying that such projections are not reliable and they are not supported by science and evidence. And basically in literature, there are no studies on, or very limited studies on the environmental impact estimation for evolutionary and revolutionary aircraft. There is no framework to assess the operational performance of them. And that's why it can lead to mislead basically the investment and policy actions toward meeting climate goals. So this is important and requires critical attention. And how to address that? Well, basically, we need to start from aircraft design, model the performance characteristic, dynamical model, then estimating the emission and environmental impact, and having a framework that can assess the operational performance of the next generation aircraft, which is completely lacking or missing the literature. To address that, I was coordinating a proposal writing for the last CESAR call, which was on integration of the next generation aircraft. And it was part of exploratory research, working area 2. And yeah, we will hear about it, I think in January, if I'm not mistaken. So I'm going to briefly present this project, which aim to address the gaps mentioned in the previous slide. So here we can see the overall concept of the project. And as mentioned, we are starting with aircraft design, dynamic performance modeling, so dynamical model for the new types of the aircraft, and then estimating emissions, local air quality, and climate impact. So in this one. And the scenarios is basically fed by another block, so different scenarios up to 2050, which we need to cover because it's a critical year or a milestone year to assess the climate effectiveness, the effectiveness of measures in mitigating climate. So once we have the dynamical model, the emission and environmental impact model for the evolutionary and revolutionary aircraft types, we need to develop concepts of operation and optimization for safe, efficient, and low impact integration of mixed fleet into airport and aerial operations. And basically here we have two layers of assessment. One of them is the detailed one or low level one, which is this level. So we put in operation mixed fleet and assess their operational performance. And we aim to provide concepts of operation, the infrastructure adaptation needed in order for seamless integration of mixed fleet. But also we have another layer of information, which is more stakeholder relevant information. So the framework here is interesting to analyze in detail what happens when we incorporate mixed fleet into the operation. But for those projections, the one that I showed earlier, we need to have lower fidelity, but a real-time or faster framework. So the idea is that we run these tools developed for airport and aerial operation for different configurations. By configuration, I mean fuel availability, technology availability, the policies, the demand, so everything. Many times, and come up with a data set. And the idea is here in this block to train a model that can provide real-time information for a given scenario. So basically, for a given scenario, we run this block 2 and 3, and we come up with some indicators, and we train a model. And then the stakeholders, policymakers, can specify the scenario and run to get in real time what would be the projection toward future. And it's super relevant because here this model is trained based on a detailed analysis of the dynamical or performance characteristic, emissions, climate impact, and also high fidelity incorporation of mixed fleet into operation. So it's supported by evidence and science, which is lacking. And then we have also another layer which provides basically this information to the relevant audience. So in this project, we were focused mainly on this. So we are responsible for the concept and optimization of mixed fleet aerial operation. And I'm going to briefly present it here. So the idea is that we try to implement a bi-level multi-agent deep reinforcement learning to plan mixed fleet trajectories in a climate optimal or environmentally optimal and operationally feasible manner. And the way that we incorporate it is basically try to take as input the dynamical performance models from block 1, the emissions model, the environmental impact model, so everything. And then we have the environment of the multi-agent deep reinforcement learning as the airspace, and we have reward function as the climate impact, air quality, and also we have some ATM KPIs such as complexity, ATC workload, or capacity demand. Then we have 2 levels of optimization. One is high level. We are given a demand, but we don't know how to distribute the available technology and fuel to those flights. So we need to have a high level that does the selection. So categorize aircraft based on the fuel, based on the technology. And then at the lower level, we have the flight planning process for each aircraft. And here we can see how it is done. And it's important to note that this cannot be efficiently decoupled to high level and low level. So we need to be in operation to see which flight to be, which technology and fuel to be used for which flight, if we want to plan the trajectory or in general strategic planning in a climate, the most climate friendly manner. And after the training, then we will have the execution phase, which we provide origin destination pairs, weather, fuel, technology, infrastructure, availability, market-based instruments, so many inputs, and then we have the trained high level and low level. So this framework would be fast, and this is what is missing. So basically, this bi-level optimization is missing in the literature. So for reinforcement learning. And this is what is one of my future lines of research to work on the foundation of multi-agent deep reinforcement learning for bi-level problems. And the other one is another natural follow-up of what I've been doing is to do trajectory planning and low-level tracking of drones through learning-based approaches. 2 approaches that are interesting is the application of multi-agent deep reinforcement learning, what I presented, and also another one that is promising is imitation learning, which is similar to a supervised learning, but we have corrections there. So it's not a static data that we use to perform optimization. And why learning-based approaches? Because we want to have something that can be implemented in a computationally friendly manner and allows for planning and tracking at high frequency. So this is also another direction. And the last one is that I had discussion with Oscar about data-driven or model-based control of flapping wings microaerial vehicles, which from control perspective is tricky because of highly unsteady aerodynamics or strong fluid structure interaction. So yeah, these are the directions that I would like to follow. So yeah, thank you very much for the attention.
Thank you, Abolfazl, for the presentation. Questions in the audience? Okay, Mario.
Okay, well, thank you, Abolfazl. Very interesting talk, and I see that there is a lot of work behind the scenes. I have a question that perhaps you answered, but I missed it, sorry. When you were discussing some scenarios where you had a flight from Frankfurt to Kiev and so on, you were suggesting different alternatives based on a parameter that controls what is the cost function, either the cost of operation or the climate effects. But I wonder, what is the sensitivity of both variables as you vary the parameter? So the cost optimal and the climate optimal solutions, what is the cost of them? What is the climate effect of them? Is it a tiny difference between them? Is it a large difference? Does it make it much more expensive to go climate effective? So this is a relevant question, I think. So if you could elaborate on that.
Yeah, perfect. Thank you very much for this question. I received a lot of comments from the reviewer in this direction about the sensitivity.
I'm not a reviewer.
Yeah. And basically, it's good to show the objective function, I guess. So here, as you correctly mentioned, we have two terms, but the sensitivity of the outputs in terms of operating costs and climate impact to the selection of this one is highly scenario dependent. For example, in one case, we may not have any climate sensitive areas, so no possibility for contrail formation. So this will be zero, the ATR.
Yeah, but for example, for this scenario that you have here.
So if we have Pareto frontier, I don't have it here, but I think Pareto frontier, so for all the analysis that we perform, that Pareto frontier that tells that for each EAIM, how we change the climate impact and operational cost. And this was also affecting the selection of EIM. It's important. And that's why for the next approach, we had something called alpha. And alpha determines the level of the optimality that we want. So before solving the optimization, we first try to solve it once, considering only cost, and the other time only climate. Then we derive a scaling factor, and based on this scaling factor, we define this alpha. So this alpha then varies between 0 and 1 and can provide solution. But I would say it's highly scenario dependent.
But in a typical scenario, are we talking about 5% extra cost of operation if you go toward the climate solution? A 10%, a 20%, does the cost of the operations become a factor of 2 more expensive? This is, what is the feeling of the cost?
So here, I think we have a Pareto frontier that we are referring to. So I don't know if you see it clearly, but we have here different solutions, different values of alpha, basically for climate impact, and the relative increase in the operational cost. Also, it's not percentage, it's absolute, but...
okay, but I can see the numbers. Okay.
If you go to the monthly analysis, the yearly analysis, you have...
Yeah. For monthly, we have it.
Yeah, the green and blue.
Yeah.
Okay, so I missed this one, sorry.
Yeah. But an also interesting thing here is that one of the measures that I presented, the market-based measures, can compensate for this extra cost. So if we assign taxes for climate impact, this is what is now the trend, then we can relax this operational cost increase and provides incentives toward adoption. So it's market-based frameworks that we are referring to. Because now on the ticket, we pay for CO2. But non-CO2, if you pay tax, then this operation can be compensated.
Okay, thank you.
Thank you, Abolfazl, for the presentation. if I understood your point correctly, the climate impact is very uncertain. I mean, there's a high uncertainty. So also in that figure, actually, you're not showing it, but they should be like large uncertainty zones, right?
Yeah.
And so if I understand correctly, your point also, all these assessments will benefit highly from better models. What do you see as an obstacle for having good models for climate impact assessments?
Yeah, that's a really interesting question. But before answering that, in this figure we have uncertainty, but it's super large, super small, so it's negligible. But the uncertainty only due to meteorology. So, but you are pointing toward a correct thing. So we know that the models that we are using, they are not accurate, and also they are not that reliable, I would say. Here we were working mainly on the framework. And that's why, for example, Amin is working toward developing a model for contrails, and also Irina is trying to work with the observation in order to be used for having better prediction of the climate impact. But yeah, the models are not reliable, to be honest. So I think this is one of the most important gaps here is the uncertainty. So this is, in my research, what we did, basically trying to use existing models and introduce uncertainty from the sources that we can model. So basically working toward the framework, but once other models are available, we can use them, try to have several models at the same time in order to enhance the confidence.
Are there more questions? No? Okay, then I think we can thanks again the speaker. It's already almost 2.